In this video, we're going to look at the common ion effect on chemical equilibrium. So we're going to do this by example. In the first example, we have a salt being added to an acidic solution. And the example question tells you have a 0.30 molar solution of formic acid. And the salt you're adding to that is sodium formate. So both the formic acid and the sodium formate have a common ion in the form of this formate ion right here. So I'm just going to write the formate ion up at the top to indicate that that is our common ion. And when you add a common ion, you change that chemical equilibrium. Now, before I got started on this equation, I went and looked up the Ka value of formic acid. And it's in the back of most chemistry texts. The Ka value is listed as 1.8 times 10 to the negative 4. And the easiest way to solve this problem is to start with an ice chart, the initial concentration. So they tell you that in the problem. You have an initial concentration of formic acid of 0.30 molar. And they want you to calculate the pH before you add this common ion, and then after. So we're going to do the before one on this slide. So I put my 0.30 molar underneath my formic acid. That's the initial concentration. Now that formic acid is going to dissociate. It's going to lose that hydrogen and make hydronium ion. Now we don't know how much, so I'm going to put, it's going to lose minus X. So my equilibrium concentration will be 0.30 minus X. Now this reaction is 1-to-1, so for every X amount I lose of this formic acid, I'm going to make X amount of the hydronium. We started with 0, and then you're going to make X amount of both of those ions because this reaction is 1-to-1. So your equilibrium concentration for both of those will be equal to X. I'm going to take this and plug it into my expression for the Ka. And the Ka expression is going to be the concentration of the hydronium times the concentration of the formate ion divided by the concentration of the formic acid. So I can now plug in those values into the equation. And I'm going to do that over here. So I have my Ka listed as 1.8 times 10 to the negative 4. Remember, I'll look that value up in the back of a book. You can get it off the internet if you choose to. And that concentration on the top is going to be X squared because X times X is X squared. On the bottom, I'm going to have 0.30 minus X. Now, the beautiful thing about this is 0.30 is quite a large value in comparison to 1.8 times 10 to the negative 4. This negative 4 here, that factor is very, very small. So if I'm going to solve for X using a quadratic, I'm going to find out that that X value is going to be so small it will round off. And anytime your Ka value is 10 to the negative 4 or smaller, you can take that minus X part and you can ignore it because it's not going to change that 0.30, that initial concentration, by very much because there's too big of a difference. So I'm going to ignore that minus X and then solve using my calculator. I'll solve. If you want to rearrange it, you know that X is going to be equal to the square root of 1.8 times 10 to the negative 4 times 0.3. Okay, that's all under that radical. And you can plug it into your calculator and solve. And that's what I'm doing right now. 1.8 times 10 to the negative 4 times 0.3. And I get an X value 0.00735. Now that's my X value. It asked me for pH. And so I'm going to put that into my pH equation, which is the negative log of the hydronium. X is the value for hydronium and formate, so my pH is going to be negative log of 0.00735, and that's going to give me a value of 2.14. So that's my pH before I added a common ion to it. Now, when I do add that common ion, I'm going to increase that amount. I'm going to increase that amount by adding this 0.1 molar, that common ion. And that's going to shift the equilibrium this way. It's going to drive it this way. And that means that this much of this hydronium ion is going to decrease. And if hydronium ion goes down, then this pH, the new pH, should go up. And that's what we're going to figure out on the next slide. All right, now we're going to consider what the pH is going to change after we add this 0.10 molar of the formate. Now, sodium formate is going to dissolve entirely, so if you have 0.10 moles of sodium formate going into solution, you're going to have 0.10 moles of the formate ion. So your initial concentration I've copied from the prior slide, from the prior problem, is still 0.30 molar of the formic acid. Well, now you have just added 0.10 molar of that formate salt. And that is going to decrease this amount of hydronium. That amount of hydronium is going to go down as the reaction proceeds back to the left. So your pH is not going to be the same. It's actually going to be a little bit higher than it was in the prior part of the problem. Now, you still are going to lose a certain amount of that formic acid. And the same amount, we're still going to consider this to be 0, and the same amount is going to increase for both of these ions on the right side of your equation. So the hydronium is going to go up by X amount. The formate ion is going to go up by X amount. Now this X is going to be much smaller than it was in the last problem. So your equilibrium is still 0.30 minus X over here, and on the right side your equilibrium concentration is going to be X and for the hydronium, and it will be 0.10 plus X for the formic acid. Now again, you're still using the Ka value. This is still an acid problem because formic acid is what's dissociating here. It's just less of it will end up at equilibrium, dissociated, because of this common ion effect. But the Ka is the same as it was in the prior problem, which was 1.8 times 10 to the negative 4. So you still have the same Ka amount. And remember that this Ka is very small, you know, and here you have a very large concentration compared to this Ka on both sides. So essentially that means that this plus X can be ignored and the minus X can be ignored. So when you start writing your expression for this Ka value, it's going to be a lot easier. And that's what I'm going to do right now. I'm going to say 1.8 times 10 to the negative 4 is equal to X on the top times 0.10, because I am ignoring my plus X. On the bottom, I'm going to put 0.30 and ignore my minus X. So I'm going to solve this algebraically, and you do that on your calculator. I'm going to pause the tape and solve it. All right, when I did the math in my calculator, I got an X value very small, and that's 5.4 times 10 to the negative 4. So your hydronium ion has decreased quite a bit from this common ion being added to the solution. So now, in order to solve for my pH, pH is going to be the negative log of the hydronium, which is, we just solved for, 5.4 times 10 to the negative 4. I put that in my calculator and I get a new pH of 3.27. So my pH has increased significantly. I have gone from a pH of 2.14 right here. Before I added it was 2.14 to a pH of 3.27 with the addition of that common ion. So anytime you add that common ion, it's going to drive the equilibrium back to the left. And in an acid situation, it's going to increase that pH. And what essentially you've developed is a type of buffer solution when you do that. And on one of the following videos, we're going to examine buffer situations and how they change their pH with the addition of acid or base.